Good evening, everybody. This is the second session on binary trees. And let's revise what we learned in the session number one real quick, and then we'll continue with some problems for this session. All right, in previous session, we talked about trees, like what trees are and how they are a non-linear structure compared to a linked list. So basically, you have a node, which can be a class, right? And each node has some kind of a payload, right? That payload is, you can call it uh, some kind of a data that it has. You can call it key, you can call it value, whatever you want to call data. And then it has link to two of its children, which are referred to as left child and right child. We are strictly talking about the binary trees at the moment. And there's no stopping that you can go to n-ary trees. They can be n number of children. And how they're represented, we'll look more into that during the graph session. But essentially, yeah, you have link to two children, left, right, and then basically, similarly, you have. Let me draw like this instead. Another tree, another tree. This is a left sub. This is a subtree, which is left subtree, and this is another subtree, which is right subtree. The first node is referred to as root. There's nothing specific about. There's nothing special about root. It's just one node from where we want to look into a tree. In our programs, in our functions, any of this node can be passed as a root node. For example, this node can be passed as a root node. And if that is passed, then we may have to examine the entire subtree underneath it. Now, how will this be implemented? I showed you a quick technique of how this will be given. And whenever this question is asked in an interview situation or an lead code, essentially this will be the class. And you will directly manipulate the object variables by writing object.left, object.right. Like there is no set or get function as such. So what I did was I created a class and I created a tree, if you remember in the previous class. And in the end, I made this tree completely a binary search tree, which I'm going to come to in a second. Then I explain some traversals, right? For any problem on tree to be solved, we essentially need to be able to move around the tree. And there are multiple techniques to move around the tree. Three of the most famous ones are pre-order, in-order, and post-order. And what they essentially mean is, in what order do we want to explore the tree, and in what order do we want to process a node? So the tree that we made in the last class, let me just redraw it here, real quick here. So the center node was 100, then this node was 50, and this node was 150, and this was 25, 75, and then this had 200 value here. Now this is a binary search tree. A binary search tree is a binary tree with a special property, and this property is that for any given node in this tree, the value of that node will be bigger than the left child and will be smaller than the right child. That's a binary search tree. A lot of problems get framed around binary search tree and its time complexity. So first, the traversals, right? We looked at the traversal. Pre-order traversal is something like we process this node first, then we process the left subtree, and then we process the right subtree. So while traversing 150, this node will not be touched until the entire of this section has been processed. Right? So because recursively, we'll just keep calling the left subtree, and then hence we'll go down all the way to the leaf. And we had in-order traversal and post-order traversal. So in-order traversal was we process the left subtree first, then we process the root, the center node, and then we process the right subtree. And finally, we had the post-order. Post order means process left, right, and then the node itself whenever you call this procedure on any of the node. Right. So those were the uh, method definitions here. If anybody has any question regarding this, you can ask me right now. All right, so this is in Python. If you don't know Python, doesn't matter. This is you will be seeing that this is pretty simple. It's as good as writing pseudocode. Now let's solve some problems. Okay, I'm gonna pick up some problems. They're very simple in the beginning, and then they may get a little tough as we move along. So recursion has to be used in binary tree problems a lot. Like pretty much all the problems of trees will be solved using recursion, except couple of scenarios where they will not be. So let's look at a very simple problem. Right, so the first problem for today is, let me write this down. Count nodes. So given a tree, so you have to write a function, right? So let's say this function is called count. It accepts some node, then it returns the number of nodes in the subtree beginning with node and including the node. So very first basic problem, like how do you count the number of nodes here? Right. So before I solve this problem, I want you to think about it for a minute and try to come up with some kind of a pseudocode if you can. And then I will come back like in 1 minute only. All right. So now I hope you got a chance to think about it. Now let me come to the solution of this problem. Counting nodes, okay? And the template of recursion kind of works for every single problem. So first, I'm just quickly going to write the function declaration. So the function that we'll have to compute would be something like def count, and there'll be a node that is passed. And this function is supposed to return the count. Right, so let me just make sure that this file is running first, real quick. And come here, 5. Yeah, it's running fine. So now the task is to count the number of nodes. How do we do that? This is the tree. We only have the first node, which is this root. So what can I say about counting? When I just look at the tree, just like that, I can easily count. But when I have to write a function, how do I do that? See, any of the recursive procedures for doing the whole traversal should work, right? If we do any kind of traversal, then essentially it's going to cover every single node. Once it covers every single node, we can keep a counter, right? But the question becomes, how do we manage that count when we are passing it along the recursive functions? So the option number one can be to have a global variable that all the functions can update. Or let me show you a simple technique. What can I say about this tree? I know that the number of the number of nodes in this tree are one for sure. This guy, this the value with the one with the value 100. That definitely is one count, right? So that's one node plus whatever is present in the left tree plus whatever is present in the right tree. Sorry, right tree. So 1 plus left tree plus right tree. So whatever is the count of this guy and this guy, because 1 is this and then this plus this. And then we can recursively apply this to this. So if I write it more simply, I can say, suppose these are the nodes, let's say N1, N2, N3, N4, N5, and N6, just generally speaking. So count of N1 will result in 1 plus count of N2 plus count of N3, right? And then N2 can be expanded into 1 plus count of N4 plus count of N5. Any difficulty in understanding this? And if there is no node present, then we essentially return a count as 0. And let's write this code, all right? So I'm going to write this function here, count. And I'm just going to say, all right, if it's a valid node, then return 1 plus count of node.left plus count of node.right. Let's stop at this position and try to run this. And I'm just going to say count of, let's say, root. So I've created a function count and I'm going to run this now. So when I run it, error, there's an error that shows up. And the error is basically that I'm trying to add an integer with a none type. Right? So this error comes from not understanding another part of the base condition. Right? So one base condition is that if the node is not none, then return 1 plus count of left tree plus right tree. But what if the node is none? Let's say if the node is none, then this value will return a none. If this returns a none back, then we say 1 plus none, and that's where the error is. Right? So the error is that we are trying to add an integer to a none. So what we do is we write an else clause as well. That also serves as another base condition. That is, if the node is none itself, then return 0. So 0 being that for a none node, the number of nodes are 0. Let's run this. Let's print it. And you get the count as 6. Let's add let's add one more node to this tree. Okay, and I'm going to keep this tree as BST. So I'm just going to say, okay, current equals to current dot write. I'm just adding one more node. And then current dot write equals to 250. So what I have done here is I have added one more node here. 250. So let's run this again, and you see that the count is 7. So count the number of nodes in a tree. If you look at the code, it's literally a 2-liner code, right? Pretty straightforward. But coming to this thinking requires some practice, like writing recursive expressions which will result in your answers. Any questions here? Or I'm going to take the no for silence. Let's take the next question. The next question is, let me redraw this tree. 100 and 50 and 150, 25, 75, 200 and 250. The next question is called mirroring. So given a tree, change this tree in place so that it becomes a mirror image of itself. So that is, this tree will become something like this: 100, 150, 200, 250, 50, and then 75 and 25. So it becomes exact opposite of this tree. And in this case, this is a BST, binary search tree. And this becomes a BST again, but it's in the decreasing order. It's exactly flip property of original tree, BST. So that's the second problem. Suppose this is a question that you have to flip every single node of a tree. So this children will be swapped. All of the children will be swapped. So how do we do that? Once again, I'm going to give you a minute. You can think about it. Try to come up with some kind of an algorithm. You don't have to come up with concrete algorithm. You can think of vaguely, like what can be done here. All right, so let's come to the solution of this problem. So the tree that we have, let's think of a smaller tree. Let's say just this was the tree. If suppose it had 3 nodes, a root, left child, right child, and we wanted to flip it, what would we do? We would just make this guy as the left child and this guy as the right child. And that will result in a flipped tree, a mirror image tree. Right, so if there is a node, let's say I'm going to write node as n. If there is a node, then n dot left and n dot right. We can do a standard swapping. We can like create a buffer node which points to this guy. Let's say buffer equals to 50, whatever that 50 node is. I'm just writing the value, but you can think of it as node 50. And then n dot left can be assigned 150, and n dot right can be assigned 50. And that can be done. Right. So standard swapping. But the question becomes tough when you have to do it recursively across the whole tree. Right. So let's do it for the whole tree. 50, 150, and let's just add 25. Suppose this is the tree. Then once again, this problem is pretty simple if you go one node at a time. All the children of every single node have to be flipped, right? Have to be swapped. So for 100, we do the same thing. Then 50, we do the same thing. Then 150, we do the same thing. Right? So essentially, we have to just visit every single node in any traversal form and then just swap the children there. And that problem is solved. Right, so let's do that. Now I'm going to write another function here. Let's just call this mirror. And it takes a node in it and it returns an answer back, which is the mirror node. Let's just say return, all right? And this function will be called as mirror of root. And before we do that, let's put this here for later on. How will you verify? Okay, what I'm going to do is, given this is a BST, what I'm going to do is I'm going to do the Inorder Traversal. Inorder Traversal on the first try should return all the values in increasing order. And if the tree is flipped, then it will result in a tree which is in decreasing order. Right, so let's just do this in order on root before and after this traversal is completed.
Sorry, can you repeat that particular part? I didn't get it.
So, for example, this tree, right? This tree, 50 and 150. The in-order traversal for this will be 50, 100, 150. Once this is flipped, the in-order traversal of this will become 150, 150. That is, it's in the decreasing order now. Why? Because this is a BST. If you flip a BST, it will become in the decreasing order node arrangement. Right, so that's how we can verify. We are dealing with a BST, so essentially it will be easy for us to do that. Let's run this code right now, right? So currently the mirror function is not doing anything. Let's run this. And right now you will see that both the traversals are returning the same answer because mirror function is not doing anything. Let's just add a print. Okay, so there you go. Because currently our mirror function is not doing anything. So now let's add some code to the mirror function. So now what do we need to do? We need to mirror. If a node exists, all right, once again, the base condition is this. If the node is none, we don't need to do anything. But if a node exists, then what we can simply do is we can swap the values. I'm not very familiar about, like, this may be available in other programming languages as well, but in Python, in order to swap two values, the most simplest way is cross assignment. So let me just show you. And you can do it however way you want. So suppose you have a equals to 5 and b equals to 3. then you can just write a comma b equals to b comma a. That essentially swap these value. Now a becomes 3 and b becomes 5. So swaps these values. Other way is basically you create a temporary variable and you assign value of a, and then you assign a, b, and then b into a. So, but I'm just going to write one simple expression here. I'm just going to write node dot left comma node dot right equals to node dot right comma node dot left. So first I'm going to process this particular node's children. Right, so node dot left. So this will essentially put the value of node dot right into node dot left, and then node dot left into node dot right. That's swap. And then I'm just going to recursively do this for rest of the tree. Right? And basically I'm just going to say two expressions. Mirror node dot left and mirror node dot right. So essentially this is a pre-order traversal I'm doing. Here in pre-order we will just printing, and then we are calling the same routine again on the left and right child. But in this particular problem, instead of just printing, we are doing something, and then we are recursively applying it on the left subtree followed by the right subtree. And this only applies when the node has some value, non-null value. Otherwise, if the node is none, then we don't need to do anything. None means that the node does not exist. So once again, we are going to run this. All right, so let's just bring this up. The previous figure that we made, this one. Right, so let's just run it and notice the output here. We ran the inorder before the mirroring and we ran the inorder after the mirroring. Right, so this is the tree. Inorder traversal means left child, node, right child. So in this case, the inorder traversal would be 25, 50, 75, 100, 150, 200, and 250. In this case, the inorder traversal would be 250, 200, 150, 100, 75, 50, 25, just in the decreasing order. And notice the output. That is the output. So we just mirrored a binary tree. We just converted a binary tree into its mirror image with 3 lines of code. Any questions?
I'm just curious how the Python validates it's a valid node when we put the code if node.
So if this condition essentially means that, all right, in Python, when you say if something, this means this condition will pass if this is not none and not empty. This condition will pass if both of these conditions are true. Otherwise, this condition will fail. That's what it is. So if let's run this through our tree. Okay, suppose that there is a tree which is something like 100, 50, and 150. Suppose this is the tree, and let's say we want to mirror it. Okay, so according to our function here, what will happen? We will call mirror function on 100. And the first line is to swap the left and right children. So what will happen is, first thing is these children will be swapped. So this will become 150 and this will become 50. That's the line number 1, like swap. Then we recursively call this on mirror of node dot left. So now the next thing that we're going to call is mirror of 150. So once we go here mirror of 150. So in mirror of 150, when we call, the very first line of the code is to swap the children. right? Swap, the two children are what? None and none, right? So it will swap these two with each other. And the next thing is we're going to call mirror of none, right? So then mirror of none will be called. Once that is called, the very first thing it's going to do is check if node, and then that check will fail, right? So nothing will happen. You will just return back here, and then whatever is the next function that you're calling, that will be called here. Is that clear?
Yes, thank you.
So is that the concept of a truthy value, truthy and falsy?
Yes.
Right?
Yep.
Okay.
So for mirroring,
Yeah.
it's like the pre-order traversal.
Yeah, we are doing pre-order traversal right now. Even in the previous example, I just want to quickly point out, this was a pre-order, right? Just don't go I wrote this in one line, but essentially what we're saying is, for this node, count 1, then do the left tree, then do the right tree. That was also pre-order.
Thank you.
So that was problem number 2, right? Some basic problem we are covering. So guys, you guys get a feel of how to write this recursive code for binary trees, and it will make your life easy. I will tell you the source of these problems. There is a very good document where these problems are listed, and I will share that on Discord. Now, one of the important things that often get asked. Okay, this time I'm just going to save this. Let's create the BST. BST, right? Binary search trees are arranged once again in a specific order. And that order allows us to search in a binary search trees rather fast, right? So for example, in a binary search tree, if a question comes, for example, this is the tree, and we want to look up whether a value called, let's say, 175 is present in this tree, right? How do we find it? So the good thing about binary search tree is that we don't have to make a comparison with every single node. The way we do comparison is we first compare the root with this value, with this key here. And we see if this is equal. If this is equal, okay, then the key is present and we have the answer is true. Let's say if it's not present, then we try to find out whether this key is bigger than this root value here or smaller than this. It is bigger than. Right? So binary search trees have a property that the left subtree, left child will have a smaller value than the right subchild. That means every single value present here will be smaller than 100. And every single value that's present in this side will be greater than, will be smaller than 100. Sorry, it will be bigger than, let me write it opposite. Hang on, give me a second. Everything here will be less than 100 and everything here will be greater than 100. Right? So if we do that comparison with the key 175 right now, and we know that 175 is bigger than 100, then at this point of time, we can say for sure that this key cannot exist in this part. It can only be present in this part. Right? So what we do is we then compare. If let's say the value is bigger than this, then we go to the right subtree to compare it. We compare 175 now with 150. And we can once again make the same question. We can once again ask the same question. is 175 bigger than 150 or smaller than 150? It's bigger. That means this node cannot be it, and neither any of its left tree here can be the answer. So the next is we go to 200 and we compare 200 with 175. Now 200 is bigger than 175. That means anything on the right of the 200 cannot give an answer. So we have to check the left. And left is where the tree ends. So we have reached to the end of the tree and we did not find the value 175. That means that 175 is not present in this tree. Let's take another example. All right, so this time let's assume that the value is 75. So once again, we will first compare 75 with 100. Now 100 is bigger than 75. That is 75 is smaller than 100. What is the conclusion that we can draw from that observation? Can anybody tell me?
It has to be on the left.
It has to be on the left, right? Exactly. So this whole thing we can discard. This right side, gone. Right? So if we were to search this in a tree of n nodes, essentially on the very first comparison, we now have to search in n by 2 nodes. All right, so now we compare 75 with 50. Now 75 is bigger than 50. That means that this part cannot have the possible answer. So we go to the next node. But on the very next step, the search space reduces to n by 4. And then we come here. We compare 75 to 75 and we get the answer. Right? So essentially, the search space is reduced in this way: n to n by 2, to n by 2 square, to n by 2 cube, all the way to n by n, where the one node is left. Right? Can anybody tell me what the time complexity of this, what this time complexity is?
Log n.
Right, exactly. That's a log n time complexity. The search space is reducing by 2 every single time, log 2n. Let's code this. Okay, suppose you want to do a binary search. Many questions are centered around this search. I will give one assignment as well on this. So let's just say def search. And in this case, you will have to pass, let's say, some kind of a node, like a root, and some kind of a key. And you have to return, let's say, return true if key is present. Else return false. Suppose this is the situation. Then once again, our algorithm is going to be something like this. I'm just going to write first some pseudo code here, okay? So basically compare the key to root. Okay, if match, then return success or true, false, whatever. If key is bigger, then search right subtree. If key is smaller, then search left subtree. Okay. So this is the recursive step here. And then basically return true if key found. If key found. And if we reach the end of the tree without key found, then return false. Does anybody have any question about this algorithm first?
You meant to write without key found, right? On line 60.
Oh, sorry, my mistake. Yeah, without. Correct. Thank you. All right, if no questions, let's code this. So first thing is that base condition is, there are two base conditions here. If the key is found, then we return true. And if we reach the end of the tree, then we return false. Those two are known situations, right? And if those are met, then we immediately return. But if those two are not matched, then we have to recursively call this function on the rest of the tree. So first thing is, I'm just going to write from here. First thing is I'm going to just write the same way. I'm going to say, let's say if node is not none and not empty. If the node is not none and not empty, that means we have not reached the end of the tree yet. So let's just put some filler statement. Else means if we have reached if the node is now empty or none, that is, we have reached the end of the tree. In that case, just return false. At least that much we can say. Now we have to do some work here. First thing is simple. We can just write, okay, if key equals, let's say node.value. Come here, check. Compare the key to the root. If matches, then return success. If this is true, then return true. If this is the case, then just return true. So we have two situations where we return true, when we know that the answer will be true and false. Now comes the third part. Let's say if this is not true, then the key can only be bigger than the value of the root or smaller than the value of root. So let's just write the second condition. Let's say else if, let's say key is bigger than node.value. If the key is bigger than node.value, then I have to recursively call search on right subtree. Else, that is, if the opposite case is true, then recursively call left subtree. This should be pretty straightforward. Now, can anybody tell me what should I write on line number 67? Like what piece of code should I write on line number 67?
Just search, and then node dot right and D.
Perfect. Right. And then otherwise, we will just write search of node.left and key. Right? It's a pretty simple routine if you notice. The key equals node.val, return true. If the key is greater than node.val, then whatever, search the right tree. Right, so we have something here, right? So each we return a true in this case, and we return a false if we reach the end of the tree and we have not found this condition to be true so far. So let's just run something on this. Let's first copy this. Okay, let's just say first we do a search on this, on let's say root with the very first item. Let's say 100. Okay, 100 is the root. We just print it. We print the answer. And also let's just put this like this. So if I run it, it should return a true, right? So this returns that 100 is true. Right, so let's run something that is not present in the tree. Just quickly, yeah, 175. Let's just say 175 is not present in the tree. So we run this, and we return a none. Why is this return none? Can anybody tell me? There's something missing in this code. The answer is, we call this function, but essentially what we need to do is we just need to say return this. Right? So otherwise, what you're going to get back is a none, right? If you don't return on every single sequence. So if you go back here, same thing as I mentioned previously here. In the count, if you don't return on all the single cases, then you run into one problem of integer plus none. In the similar way, you return. Let's run this. And now you have false. Let's run another case here. Let's just run some edge conditions here. What is this tree? Suppose we need to find 250. 250, and then let's say 250. We run this and we get a true. Let's also do one more thing. Okay, let's just print whatever we are searching. Okay, so let's just say if node, then just print node.value. So this will give us the nodes that are being searched for each of these search. All right, so let's just run this. So for 100, one search was fine. Right? For 175, first 100 was searched. Notice, first 100 was searched, then 150 was searched, then 200 was searched, then 175 was searched. Right? So 100, 150, 200, and then 175. Something here was searched, but it was not found. Similarly, for 250, you will notice first 100, 150, 200, 250, and then that's the answer. So you can also check which nodes are being searched. Yes.
I have a question because I think maybe I messed up something, but it doesn't work when I look it up for number 75.
For the 75, okay, let's just say this is 75 and this is 75. And let's run this. Let me just remove this print here. It's too verbose right now. So 75 is true. So check one thing, maybe this combination is correct, right? And then you're rightly calling right and left. Make sure that this is correct. Or if it does not work for you, then just post your code once again in Discord. We can take a look after the class.
And also use the while loop instead of the recursion.
Why did you choose to use a while loop?
Because I'm thinking we do while node and then keep checking if the left node is the key is bigger than the current node, and then if it's bigger than, so we gonna node equal node dot right. Is that correct?
Yeah, so in this case, actually, while may work. Basically, you're saying while the node is true, then this check, right? That's what you're trying to do.
Mm-hmm.
Are you adding a break correctly? Because even if this is found, your while loop may still continue.
Yeah.
Right? Just make sure that your breaking condition is correct. And then even though it is found, your control may come out of the while loop and then return false in the end.
Mm-hmm.
But we can check. We can check after this. We can talk on Discord.
Thank you.
Yeah, let me cover one more problem. Actually, I want to cover two problems. Let me cover one at least. Okay, this type of problem is also very common in interview type of settings and will serve as a template as well. You have a tree. All right, suppose this is the tree. A, B, C, D, E, F, G, H, and I. Suppose this is the tree. And you're asked what is the maximum depth of this tree? What is the maximum depth of this tree? So what is the depth of tree? So depth of the tree means the maximum distance you have from the root node to any of the leaf node, to the lowest leaf node. So that is the depth of the tree. We reach, so this is called, let's say, level 0, whatever. Or this is, let's say, called 1. This is 1 depth. Then this level is 2 depth. Then this level is 3 depth. This level is 4 depth, and this is 5 depth. So clearly, in this type of a problem, what you have to do is you have to go down all the paths. All right, so path number 1, let's say, is this. The path number 2 is this, and then this. Sorry, let me do it the other way. This, and this. That's path number 2. The path number 3 is this, and this, and this. Path number 4 is this. You have to compute the depth of every single path, and then whatever is the maximum you have found, you have to return that as the answer of the maximum depth. And surprisingly, recursively, this will be pretty easy to code as well. Right? Clearly, you can form an expression right now, if you think about it, that the depth of, let's say, A will be what? Will be 1 plus whatever is the maximum depth of either this or this. Right? So you can write that let's say the max depth of A will be equals to 1 plus the max depth of B or the max depth of C, whichever one is the maximum. Right? And then similarly, this max depth of B will open as 1 plus max depth of either D or max depth of E, whichever one is maximum of those. Let me just rub this and write it slightly better. So once again, what is the recursive expression I'm going to write? I'm going to say max depth of A. I don't know what this is, but I know this much, that it will be 1, which is its own depth, plus the max of either the left subtree depth or the right subtree depth. How do I calculate the left subtree depth? I can call again the max depth of B or the max depth of C. And then max depth of B, I don't know. But once again, it can be recursively evaluated as 1 plus max depth of its left or right subtree. Any questions with this so far? So let's write the code. Okay, suppose that in this tree itself, we are going to write a method called depth of this tree. Okay, and suppose it takes a node and it's going to return an answer back. So clearly, if first thing first, let's write the base condition this time in the opposite direction. I'm going to say if not node, sorry, if if not node, then return 0. That is, assume that you are given a tree which is none. That is, there is no root in it. In that case, what is the depth? The answer is 0. Or if you have reached the leaf, then there can be no more depth after that. So that is the 0. Right? If not node, then return 0. Else, return what? Return 1 plus max of, right, depth of either node dot left or depth of node dot right. Look how elegant this is. Let's see if it works. What we are writing is basically if you have reached the empty point. Let's say if this was one node, assume that the tree only had one node, okay? And it had it had two nodes, a node root and a right child RC. Then in this case, the maximum depth of the tree would be what? First, we will go to the root node. And the root node is not none, so we will say the depth is 1 plus maximum of node dot left or node dot right. So node dot left is what? None, right? So we'll say if the depth is 1 plus max of depth of none or depth of right child. So when depth of none will be called, and we will say that if not node, then return 0. It is none already, so that value is true, and then we return 0 for this. And then we say depth of right child is 1. Evaluates the same way. So the height becomes 1 plus 1, which is 2. And this goes on recursively for every single level. So let's apply this to our tree. The same thing. I'm going to put this in the comments. And let's go back here. And let's say depth of our tree. Let's say root. And let's print it. Let's run this. And the answer is 4. So that's our depth of our tree. All right, let me just draw the tree again real quick. And let's see how the depth came out. So basically 100, and then that was essentially, I think this was the branch, 150, 200, and then 250. That was the maximum depth because this was just 50 and then 25 and then 75. So that was the 4 that the answer came back. We can also do this some kind of a, let's say, subtree. Just do depth of, let's say, root dot left. So if the root dot left was the real root, then what would be the answer? The answer would be 2, right? So the maximum depth of just this guy is 2. Any questions?
So this is considered in order as well.
Is this considered in order as well?
Yeah.
Not necessarily. This is pre-order as far as I see, because
yeah.
you see, for this particular node, we are saying
right.
1 plus, left and then right, something like that.
Right.
Yeah. You can break these statements always, right? So you can always say, instead of this, you can write something like this. Okay.
In the middle.
Left depth equals to, let's say, depth of left. And then right depth equals to this. And then you can just say return max of left depth or right depth. 1 plus whatever, like that. But I write usually one expression for this, all of this, so it doesn't matter. I write like this. So we solved 4 problems right now. I had one more problem. I'm going to put a video maybe for that. But the next problem in the queue is to print all the paths. Okay, so given a tree, let's say this tree, okay, A, B, C, say X, Y, Z, and D. Then the question becomes print all the paths of the tree from root to leaf. So how many paths are there from root to leaf? There is one path is A, B, X. Then another path is A, C, Y, and D. And the third path is A, C, Z. That's one path, 2 path, and third path. So for a given tree, print all the paths from root to leaves. Right? That's another type of problem. It adds a little bit of complexity in the sense that you have to maintain a separate buffer to keep track of the paths. Try to attempt this problem yourself. See if you can get through this problem. Now, I would like you to think about a couple more problems, all right? After this, based on this session, we looked at a problem about binary search tree in which we were looking for the key and the value pairs. Sorry, my mistake. So we were looking for whether a key is present inside a binary search tree or not. Suppose I extend this problem a bit more and I tell you that given a key, find the node which has a value which is closest to key. All right. Find a node which has a value that is closest to the key. Okay. And if the key is found, then you can return the node itself, because let's say if I ask 50, then the answer would be this node because the distance is 0. 50 minus 50 is 0. But let's say if I ask 110, right, then what is the minimum distance that we can get? The answer would be, I guess, 100 itself, because the distance is 10 from 110. Right, so the key, find a node which has the least distance from the given key. Okay, it's exactly this algorithm, but it's a slight twist to it, so you can practice.
I have a question. So
Yes.
in the binary search tree, you don't have any duplicates, right?
Yeah, there is no duplicate. There is no duplicate in a binary search tree.
And I have one more question regarding to the return keyword when you're using the recursion.
Yeah.
Is that every time you use recursion, you're gonna use the return keyword? Like I quite confused about recursion because sometimes I see people use return and sometimes I didn't see them